Yes, yes.
Just one person per group.
If you want to come both, 2 or 3, that's better. But at least one. So the person who comes can talk about the experiment to the other person in the group. But if you want to come both or the 3 members in the group, that's better. Okay. I'm worried about the person who are not here. They are not from Guayaquil. Miss Lopez, are you in Guayaquil?
Good afternoon, doctor. Yes.
Oh, so you are Guayaquileña now, right? Mr. Carrillo, are you here or what?
Yes, I'm here in Guayaquil, doctor. No
Okay,
problem
good.
for me.
Mr. Barba. Where are you? Mr. Barba, can you hear me? No.
Yes, I'm in Guayaquil. Now
Okay, you're
traveling.
in Guayaquil. Okay,
Yeah.
good. Miss Vega, Miss Vega. Miss Vega, can you hear me?
Yes, doctor.
Where are you?
Guayaquil.
Oh, man. Everybody's Guayaquileño these days. Miss Matias, Miss Matias. Matias, can you hear me? Oh, we have problems with her. Can you say something about in the chat? Are you in Guayaquil, Miss Matias? Can you come tomorrow to the test? I'm just asking. Oh, you're in Salinas. Okay. And when are you planning to come to Guayaquil? On Thursday? When are you planning to come to Guayaquil? Because I understand tomorrow. Okay. At what time? Okay. Yeah, we understand that. There are some people who have problems traveling. Yes. Okay. Good. Mr. Mr. Matute.
Yes, doctor. Hi.
Are you from Guayaquil?
Yeah.
Okay. So you're here. Who else? Mr. Estudillo, are you in Machala?
No, doctor, I'm in Guayaquil.
Other Guayaquileña. Good. Mr. Ramon, where are you?
Hi, doctor. I'm in here in Guayaquil.
Okay. So, again, for those of you who are in Guayaquil and can come tomorrow at 8 a.m., okay, I'm going to say something about that at the end of the session, okay? Now, today I would like to close this chapter on the hydrodynamics, and we're going to say a couple of words about waves, okay? One of the parameters that we're going to be describing or describe the way to calculate is the wave celerity, okay? And tomorrow, you will be able to generate waves with different frequency. And for each one of the frequencies, hopefully we will be able to measure the celerity. And the celerity will depend on the frequency and on the wavelength. So all of those are well connected. Okay, so we're at the end, I'm going to describe that. But before that, we have to say a couple of words mathematically, okay? So that's the idea behind this session. Also, at the end, I would like to answer questions about the homework, if there is any. And then I will describe, as I said before, what's going to be tomorrow and Friday and Thursday, of course. Okay, so that's the agenda for today. Miss Ayo, can you see my screen?
Yes, doctor.
Full screen now?
Yes.
So this is the last point in this chapter. It's about characteristics of the waves, gravitational waves, okay? There are many waves, and in this case, the gravitational effect is the origin, is the source of this motion. That's why we call it gravitational waves, okay? In this case, we're going to be working as a 2D problem. That means that I'm going to show a plan XZ. That means that in the Y direction, there is no dependence, because that, I think, the profile, the wave profile that you see in the plan is the same for any Y position. Okay, so that's something that we're going to be assuming. Okay, this is the description of the general problem. Okay, immediately you see that inside the domain, in this case, the domain, see, this is the water, this is the air, okay? One of the problems here is that inside the domain, we're going to assume that this equation is satisfied. People, immediately you see this, you think that there is no what? Anybody?
Viscosity.
There is no viscosity, exactly. So it's a irrotational flow. And also the density is constant immediately. You don't need to expect that. You simply see Laplace's equation. It means that the continuity is satisfied with these two restrictions, no viscosity and the density is constant. Okay, so in the bottom here, we're going to have satisfied the no penetration condition. That means that the velocity in this direction is zero. Okay, so d phi, dz, and the bottom has to be zero. Okay, now this is inside the domain, and this is another surface, another boundary. Now, in this boundary, I'm going to explain in the next slide these two conditions. Okay, so we are going to satisfy the boundary condition. See, this is a very delicate boundary condition because it's moving. So in this boundary conditions, we impose not two conditions, but two half conditions. Okay, and at the end, when we solve this, we're going to end up with the condition. You will see that in a minute. Okay, now here, this is the function. Okay, this is the function that specifies the profile of the wave. Okay, now since this is cosine, you can see that this is equal to e to the I omega t minus kx. Okay, because you take the real part. And z0, this is the amplitude of the wave. Okay, usually oceanographers, they prefer to express not the amplitude, but the height. Usually that's because when you stay on the deck of a ship, right? And let's suppose you try to see how high is the wave. Okay, in that case, you should try to see the distance between the crest and also the intermediate line. But that intermediate line, that's the x-axis, doesn't exist in the real world. So it's like you have to imagine, okay, you see the crest, and here is the throw of the wave, and in between, you have to see the x-axis, and then you have to see the difference. So it's much easier if you try to see what is the crest, what is the throw, and the vertical distance is twice the amplitude, and that's what they call the height. Okay, so usually oceanographers, they prefer to specify the wave amplitude. Instead of that, they call it wave height. So the wave height is twice the wave amplitude, okay? But we got a lot of information from them. That's why we have to accept the way they call it, okay? And here, you see that there are two variables here in this expression. There is time, and there is also the x position, right? Okay, so that means that if you take a picture, the time is fixed. And in that case, the x changes. So if you change the x, okay, this x here, okay, that means that you are changing this angle. And as you change this angle, the cosine has the harmonic shape, okay? Similarly, you can fix one position. Say, for example, I want to analyze what happened here. So in this case, the x is fixed. And then you start seeing what happens as the time goes by. That means that this time will change. So if you change this, again, the cosine will make you go positive, negative, positive, negative. So you are in the same x position, but you go up and down, up and down, up and down. So you have to consider both dependencies, okay? Now, this is a negative sign, and we will explain that in what cases you use negative and in what cases you use positive, okay? And as I said before, as you can see in the y direction, there is no dependence. That means that if you change in depth, you go inside the paper or outside the paper, there is no change. Okay, the same profile, you will observe it as you change in the y position because it's a 2D problem. Okay, now the solution for this is something which is very well known. It's something like this. Okay, so we have an A bar, just to emphasize that this is A bar is a complex coordinate, parameter. E to the I omega t minus kx. And you see immediately that this term is the same as this one. Okay? Remember, this function, zeta, is the wave elevation on the surface. And this phi is the velocity potential inside the domain. What are the units of zeta 0? Mr. Zambrano, what are the units of zeta 0? Zeta 0. Meters, yes, length. What are the units of A bar? Miss Vega, what are the units of A bar? This is length. Miss Vega, what are the units of A bar?
Length square over t.
Over time, yes.
Over time.
Yes, yes. Okay, so that's difference, but there is some dependence. Okay, now, and finally here, please be careful because the I, the harmonic dependence, is affecting the time and the X. But here you see, you get KZ without I. So this is a real term. Okay, now, please, there are different books, different references and all of that, right? In this case, this is the reference that we're going to be using. Z is positive upward. That means that if you go downward, the Z is going to be negative, right? What happens when I have a negative, a very large negative value? What happens with this term? It's Miss Astudillo. What happens with this term when you go inside here at the bottom of the C? What happens with this term here?
Reduce.
What? I'm sorry?
Reduce, doctor.
Yes, yes. It gets closer to zero. You have heard the term, right? Increases exponentially. In this case, the exponential is here, but the Z is negative. So this term here very quickly goes to zero. Okay, so when you go to the C, right, it comes a very large wave, right? What do? You swim very close to the bottom. And this is the term that helps us because the e to the kz is very small. So you don't feel, if you are very close to the bottom, close to the sand, you don't feel the motion because of the wave. Okay? So every time you go to the sea and take a coochie, right, and you go very well below, remember, e to the kc, that's my help. Okay? That gets very close to zero. So basically, there's no motion in the bottom. Okay? If you're close to the surface, e to the kz is very large, and you get shaken. Okay? All of that. Now, before we go on, it's your responsibility to check that this function satisfies the Laplace's equation. Okay? I'm not going to do it. I did it once, it's enough. Okay? What else? You have to check that here, this condition is satisfied. Okay? So this, you have to check. This, you have to check. So the only condition that we are going to be mentioning here is this. Okay? Is this. So we're going to say something about that because that's very interesting and gives us a lot of information. Now here, in this function, okay, A bar is the amplitude of the velocity potential. Okay, omega is the frequency. This is 1 over time, so this is radians per second. Okay, K, we're going to explain that in a minute, and it's what we call the wave number. Just by inspection, Mr. Matute, what are the units that you would expect for K? Mr. Matute, what units would you expect for K? Mr. Matute, are you there?
1 over length.
Yes. So when you multiply by x, which is length, you get radians. Okay? And you have that dependence on time, x, and z. It's a 2D problem. So we depend only, especially, we depend only on x and z. That's why we call it a 2D problem. Okay? Now let's go on and let's try to describe some of the characteristics. Okay, we're going to say something about, okay, we have this negative sign, omega t minus kx. And you immediately think, why don't we use plus? There is some physics behind that, and we're going to explain that. Now, what is k? I don't know. Let's see what k is. Okay, now, things like that. Okay, we're going to be describing this afternoon. Okay, now, free surface condition. These are very, very delicate matter. Okay, you are supposed to be, you are supposed to check that this function satisfies Laplace's equation. You are supposed to be, you are supposed to have checked that this function satisfies the boundary condition at the bottom. So the only condition that we need to discuss is this, is the free surface boundary condition. Okay, now, how do we do it? We do it in two parts. There are no two boundary conditions. There's only one boundary condition, but we express it in two pieces. More or less, that's the physical idea. Okay, the one is the kinematic boundary condition. Okay, so if we have something like this is a wave. Okay, remember that this function is zeta. So that's the function that describes the wave elevation. Okay, now, this function tells me how the surface goes up and down, okay? So in this condition, kinematic means something related to velocity, okay? Let's consider a particle here. Let me change color. Let's use a yellow. Okay, so the yellow, that's one particle, a fluid particle, which is on the surface. Okay, and let's consider that this particle is moving upward. So this is moving upward. Okay, now, if the velocity of this particle is not the same as the velocity of the surface elevation, okay, what happens? Okay, if one is larger than the other, okay, so you can either have like a delta Dirac, or you can have like a hole. So to avoid that, because you see that the wave's elevation is uniform or is continuous, you have to have both moving at the same path with the same rate. So the wave profile moves upward, and at the same time, a particle moves upward with the same rate. Otherwise, the particle can jump outside the water. Or he gets behind, there's going to be like a little hole. And none of those is possible because we are seeing the surface is correct. So we need to have both moving with the same rate. So the wave of this particle, right, since this fluid is just the gradient, the phi of this z. So this, on the right-hand side, I have this equation. Okay, so this is the velocity of the particle. Remember that since we are in the potential flow, the velocity is equal to d phi dx in I direction plus d phi dc in k direction. So this is the component in the vertical direction. And on the other side, this has to be the velocity of the wave disturbance. Okay, so the surface is moving up and down with this rate. Of course, in the vertical direction. Now, you see that you are trying to find phi, right? The function phi. And right now, you are giving me a boundary condition, but in this boundary condition, you include another function, zeta. So you say this is the condition, but in the condition, you include another function that we don't know how much it is. Okay, that's why I said before that this is like a part of the boundary condition. Okay, what's the other part? The other part is what we call the dynamic boundary condition. Okay, so let's remember the Bernoulli's equation. So we have the pressure plus rho phi of t, so rho g z, and it's equal to constant. We have linearized. Now, what we're going to assume is that on the surface, so on the surface, Z is equal to zeta. The pressure is constant. Now, you can start arguing, okay, let me try to put something like down here. Okay, let's suppose that I have the wave here, right? You can say, wait a minute, if I stay here in the throw and I stay here on the crest, okay, if this is the atmosphere, okay, this height is different than this height. And the pressure, because of the air, the weight of the air is different, right? But you cannot say that H1 and H2 are very, very, very large, right? So basically, the height of the wave is so small that basically H1 and H2 are the same. Okay, so H1 is like maybe, I don't know, kilometers. And the wave height is probably 2 meters, right? So when you are on the crest, H is, I don't know, 10 kilometers minus 2 meters. And when you are on the throw, it's 10 kilometers plus 2 meters. So basically there's no difference, right? So we're saying is that basically when Z is equal to zeta, the pressure is basically the same, atmospheric pressure, okay? So that means that this term here, we can move it to the right-hand side, right? And we have there two terms, which are constant, okay? So all what we need is this in order to have, to satisfy the dynamic boundary condition, okay? Now, in both terms, we have rho, so we can cancel, and we can say simply something like this, okay? Instead of Z, we call it zeta because we are evaluated on the surface. We cancel rho, and we can say that zeta, that's the wave elevation, is equal to minus the derivative with respect to time of phi divided by the gravitational acceleration. Okay? So now we can replace this zeta. We can replace this zeta. Can put it in here. So I have minus phi of t divided by g. So here I will have minus phi 1 and 2. There's going to be minus phi tt divided by g. Is equal to that. So we can move both terms on one side, and this is the result. Okay, so that's the combination of the two terms. Okay, now, if I have this is the function that we are using to solve this problem. What's going to be the derivative, the second derivative with respect to time? Mr. Zamora, what is this term equal? If I assume that this is phi, what is this equal to? Mr. Zamora.
It will be omega squared.
Phi. I'm missing something there, Mr. Zamora.
No. I?
Minus?
Minus, yes. Because I have I omega squared, and the I squared give you minus 1, yes. And what's going to be the derivative with respect to Z? Isidro. The derivative of phi with respect to Z, Isidro.
Yes. Use any expression.
I'm not listening to you.
Can you hear me?
Mr. Carrillo, can you help us? Mr. Carrillo?
Yes, doctor. Plus gravity multiplied por K.
So it's going to be, well, I'm just asking this. So it's going to be K times phi.
Yes.
Okay,
Y-
now I have the phi in both terms. So I cancel. So I have minus omega squared plus GK equal to 0. And that's what we call the dispersion relation. Because this expression, you will see that in a minute, will tell me that different waves have different, with different wavelengths, have different velocities. See? So if we start on the left with a wave like this, and a wave like this, okay, and we add, okay, what's going to happen after some time is that this one here will reach first. So we're going to have something like this. Then we'll have that. And eventually, like here, we'll have this one. So it's like they are separated. And you will see that the longer wave will travel faster. So that will separate from the shorter and from the shorter waves. That's why we call it, well, they call it dispersion relation. Okay. Now, this is the case when, I'm sorry, let me change color because this is something that I forgot to mention. This solution is adequate for deep water. Okay, if you have a limited draft, limited depth, okay, in that case, the solution, the function here is different. Okay, and you will find in that's something that you have to do to prepare the report. Okay, in the lab, of course, the depth of the water, it's right now it's about 20 centimeters. Okay, so when you make it oscillate, there will be some dependence on the wave height. Okay, because it's not very deep, of course. So it is quite likely that we have some dependence on the water depth on the velocity. So you have to find a function similar to this one, but not exactly the same in the literature in order to find the solution for this problem, okay? When the water depth is not very high. This solution is specific for this case, okay? And if you find this other function for for the case when the water depth is not very large, okay, you can use that function and replace it into here to obtain a different dispersion relation, okay, for the cases that you are analyzing, okay? But in this case, for very, very high depth, this is the solution and this is the dispersion relation. Omega squared is equal to kg. Omega squared is equal to kg. Everybody repeat with me. Omega squared is what? Kg. I'm not going to give it to you in the evaluation. So you have to remember that. Omega squared is equal to?
kg.
Okay. Remember that, please. And don't start making that in your hand, okay? Omega squared is kg is quite useful for this area of engineering, okay? Omega squared is kg. Now, omega, you know what it means. It's frequency, so it means how fast you complete cycles. What is K? I will explain that in a minute. Okay, G, of course, is the gravitational acceleration. Okay, so what we have done right now is that if we set the K factor equal to omega squared divided by G, we have solved completely the problem, because we have checked, or you have to do it, that it satisfies Laplace's equation. We have checked that it satisfies the no penetration condition at the bottom, and we have set that if K is equal omega squared over G, then the two pieces of the boundary condition on the free surface are satisfied. So right now, if K is equal to omega squared over G, that's a solution for this problem. Okay, so they were really smart people. They were really smart. So they left this constant in order to fit it and satisfy the boundary condition on the free surface. They were really smart. Okay, now let's start by that, and let's see what some of these characteristics are. First, right now we have a bar, and that's the amplitude of the velocity potential. Okay, but we suspect that there has to be some relation of that with zeta zero. Zeta zero is length, and physically, if I ask you, if I tell you, for example, you read in the newspaper, right? For example, that we are receiving a wave train, and the average amplitude is 1.2 meters. And you immediately have a general idea, right? 1.2 is about that. In height is like that. But if I tell you we're receiving a wave train with amplitude of the velocity potential of 50 meters square centimeters per second, do you have an idea of how big is that wave? No. So we're going to connect these two, okay? And this is the way we do it, okay? Remember, this is the dynamic boundary condition. That means that the pressure over the whole system, over the wave elevation is uniform, is equal to B0. And what we do is we replace the wave elevation, zeta, and also phi, the boundary, the function for the velocity potential. Okay, so we replace this into here, we replace into there, and we can see immediately that this term will cancel. And what we can do is we can assume that in this case, Z is very small, because we expect the wave elevation or the wave amplitude to be small. So this term here will be equal to 1. Remember that here you need on the right hand side, you need to differentiate with respect to time and divide it by G. Okay, and from here you can deduce that the I bar is equal to IG zeta 0 divided by omega. So right now you can see that we have expressed A bar, which is a very difficult to visualize parameter, in terms of something which is more physical. G zeta 0, that's the amplitude of the wave, and divided by omega, which is the frequency. Okay, now after you have this, okay, you can replace this into the expression for this, and you can have completely expressed the velocity potential like this. So instead of a bar, we have it in terms of the amplitude of the wave train, which is something much more physical. Okay, so that's something which is quite useful. Now, the next thing is, remember, we included this term as negative. Why? This is the explanation. Okay, now let's suppose that we have our system of reference system X and Z. And let's suppose that we have a wave at any instance of time, okay? And this is the wave that we have right now. Okay, now this point here is at position X. Now, let's suppose that sometime after that, we determine the new position of the wave. And the new position is here. And this is a key, okay? Right now, you see here that I originally in the blue, I was on the crest. And let's suppose that you keep on the crest of the wave. So right now, you are here. So you are moving a delta X pointing to the right. That means delta X is positive, okay? Now, let's see now in our function. This is the wave elevation, okay? The wave elevation has this form. Now, the time from the blue has increased to t plus delta t. Forget it, the time always goes in the right direction, increases all the time. You cannot go back to your past. Forget it, that's just for movies. Now, if we increase X, what happened is that this angle is kept with the same value. If this angle keeps the same value, that means that you are in the same relative position of the wave. That means that you are in the crest and you move on the crest. But the most important characteristic here is this delta X is positive. So if you want this delta X to be positive, then you need this sign to be negative. So this term increases, this term increases, and the difference allows you to keep the same value and to move with the wave. So in general, when you see that these two terms are separated by the negative sign, that means that the wave moves in the positive X direction. So negative means wave moves in the positive X direction. And you can reason what happens when you use plus. When you use plus, that means that the time increases, and to have this combination with the same value, if one increases, you need the other to decrease. That means that X will decrease. If X decreases, that means you are moving in the negative X direction. As simple as that. Okay? So if you use negative sign, that means that you are moving, the wave is moving in the positive X direction, and the opposite is always true. What else? What's the meaning of the constant K? Okay? And in here, let's suppose we take a picture, okay? So that means that the time is fixed, okay? Let's take a picture. Tomorrow, this is something that you're going to be doing, Okay, you're going to take a picture, and in the picture, you will be able to see the profile. And in the profile, you're going to see this characteristic, this lambda. See, so time is fixed. Okay, so let's suppose that you are here in this position, and you move a distance lambda up to here. And you see that the profile completes one cycle. That means that if you want to go along this motion up to a new position in X, you have to increase this angle by 2 pi. That means that K X plus, how much have you advanced? Well, you have advanced a distance lambda. That has to be equal to 2 pi. If you increase by 2 pi, then you will have the same value for the cosine here will be recuperated here. That means that K is equal to, you put lambda to the other side, is equal to 2. I'm sorry, there have to be an increase in at any angle. Any angle, let me write it. The increment is 2 pi, not the total value is 2 pi, I'm sorry. So it's equal to Kx plus 2 pi. Yes, so K is equal to 2 pi divided by lambda. And this is what we call the wave and as somebody said, the units of that is 1 over length. So when you multiply that by X, the result is going to be radians, as it should be. Questions so far, people? Questions about these waves? Let's take a 5-minute break, and when we return, there will be some words about how to calculate the celerity, and also it's going to be interesting. But the wave moves with a certain velocity, but inside the domain, inside the fluid, the particles are also moving. So we have to evaluate both. The celerity, that's the what we call the surface disturbance travels on this free surface. And also inside the fluid, there's going to be some velocity. We have to calculate both. Okay, so let's take a 5-minute break, and when we return, we will do that. Misayo, would you please stop the recording?
Okay, doctor.
Thank you very much.